Hey everyone, back in a new awesome video, and today we're gonna continue with our series about electricity and magnetism. Today we will start exploring DC circuits in a series of 4 videos on this topic. First of all, we will introduce the terminology and how different elements of these circuits in the diagrams that we use are called. After that, we will state and understand the famous Kirchhoff Circuit laws. And finally, we will understand the difference between current direction and circulation direction. So, let's start! Alright, one of the first things that we need to do is to understand all of this terminology that is portrayed in this simple circuit. There's 4 different elements that we're going to be starting to use in DC circuits, and there's also 3 different sort of conductors or different elements of wire. Basically, this part is regarding the elements that are drawn in red, and this part is regarding the elements that are drawn in black. So, first of all, we see that there is 4 different types of elements in red. The most important one of them, in this case, it's usually the battery. Because if there is no battery in a circuit, it's probably not gonna last too long unless you have a charge capacitor, and it's not really interesting. So it's a very important item and terminology thing to know. We have batteries. We observe that the battery has a positive side and a negative side. Apart from using the different signals, note that the positive side is always bigger than the negative side. On the other hand, in a capacitor, and that's kind of a spoiler, the positive side and negative side are of the same sign, and we will denote them with the signs. As we have mentioned it already, we can also write the capacitor, as it's also a very important element in DC circuits, and one that adds the more dynamic behavior of these circuits. Then we have resistors, which are an integral part of each circuit, as they represent the fact that our cables are not ideal and they have some loss of energy. And finally, we have the switch. The switch allows us to start and stop our circuit. And when this circuit and the behavior of it is time dependent, it's very important to have a switch in our system so that we can set some specific time to be time 0. Now that we understand these elements, we need somehow a way to connect them in different ways, and that is where our conductors, the black parts, come in. First of all, we have the simple lines with corners and everything. Those are wires, that's how we call them, and we idealize them as ideal wires so that there's no energy loss in those wires, and the only energy loss is through resistors. So really, in this diagram, we should have an extra resistor over here to portray the energy loss of this part of the wire. Then we also know that circuits not only go in one direction, sometimes they bifurcate and they join back again, and for doing that we need these little elements that are called junctions. Even though in this drawing we've only used a junction that has one start and 2 exits, or 2 starts and 1 exit, in reality junctions may have as many entering points and exiting points as we want. And that could be done also by the use of three-way junctions, just one after the other. So it's really the exact same thing. Last but not least, one element that we need to consider but doesn't appear directly on the picture is branches. Branches are the different parts of the circuit that are between two junctions, and they may have elements on them, and they are very important when dealing with them. For instance, one of the requirements that we have for a good DC circuit to be possible in reality is that on each branch we need to have a resistor, something that this drawing doesn't have, so that we make the approximation that the wires are ideal, but we take into account that there's a resistor that is losing that energy, and the wire is really losing that energy. Now, note that in this circuit we have three branches. The numbering is not important, but we will have this first branch from this junction to this other junction, this second branch between these two junctions, and this third branch between these two other junctions, but through the other side. These are the most important elements and nomenclature that you need to know to understand DC circuit diagrams. Now we are ready to state Kirchhoff's circuit laws, which are really important when dealing with circuits. The first law as we see, first Kirchhoff's circuit rule states that the sum of all currents entering a junction must equal the sum of all currents leaving the junction. If we think about it, this is no other than a statement about conservation of charge. If there is charge entering the junction, as we saw by our definition of current in our previous video, we have that all charges entering, which is what really current mean, to exit, there cannot be charge being created out of thin air, and there cannot be charge being expelled from the system at any point. So in every junction that needs to happen, on our elements, different things may happen, such as charge accumulation or a charge not creation, but like taking charges away from some metals, etc. But at junctions, in the way that we portray them in our circuit diagrams, there cannot be any charge creation or destruction. Therefore, the first Kirchhoff circuit rule must apply. Now, on to the second rule. And we have the second Kirchhoff circuit rule that states that the voltage difference across the circuit loop must always equal zero. What this means is that if we start at a point of a circuit loop and we go around it, adding all the different voltage differences, across the different elements, then when we come back, this total sum must equal zero. And it's really intuitive to understand why. If this voltage difference wasn't equal to zero, we would have a particle that may go around the loop, come back, and stay at the same position with more energy than it started with, and the entire system has not absorbed energy. Therefore, what we see is that this is a statement about conservation of energy, because any circuit that doesn't obey this law would be able to create infinite energy. These two laws are very important, and they allow us to see if we went wrong at some point when analyzing our circuit and finding different currents at points and the voltage difference, etc. Therefore, it's always important to keep in mind these two laws so we can double check our work when working with circuits. Alright, now we are ready to start explaining in general how the process of analyzing circuits is. On more following videos, we will state how we can treat different elements, but for now we're just going to stick to the general guidelines. Imagine that you have a simple circuit. The first step is to always choose a direction for current. At first glance, this might seem like an easy task. As you know, current always flows from positive to negative, so it's obviously gonna go in this direction. I'm sorry for forgetting to put different variables. However, this task is not always as easy. Imagine that we had a circuit as such as this one. In this case, it's not as easy to determine in which direction current is going to go. Is it going to go in this direction, in the other, which battery is more powerful, and if we have more elements, loops, it's going to be really complicated. So in general, we just choose one direction, more or less by intuition, and then we carry out all of our calculations. If in the end this current ends up being positive, that means that we choose the correct direction. If we get a negative value for the current, it simply means that the current is going in the opposite direction than the one we set. Once we have established a direction for the current, now we need to establish a circulation direction. This needs to be done for every single loop that we find in our in our circuit, sorry. Usually, we will choose our circulation direction to be the same as the current direction, but sometimes this is not possible. In general, we will denote it by a green loop in our illustrations and CD. Then the circulation direction will be really important when dealing with different elements. Imagine that we have some part of our circuit and we consider what is the voltage difference across this element. But there is two possible answers. This is why we use our circulation direction. This circulation direction allows us, if we choose this for instance, in this direction, to establish a before and an after. And then, by convention, as we chose this circulation direction, the change in potential is going to be equal to the potential after minus the potential before. In the following videos, we'll see how we can apply this rule and these other rules to different specific examples that will get more complicated through time. Also, once we learn more about magnetism and different other parts of electromagnetism, we'll be able to introduce different elements on our circuit, such as AC generators, inductors, etc., different things. And this background will be really useful when dealing with these new types of circuits. That is all for today. I hope that you understood everything and that you got a sense of the terminology and also how in general we deal with analyzing DC circuits and circuits in general. Any doubts left, you may ask them in the comment section and I try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome.